Okay, last time we spoke about the equation delta G is equal delta G in the standard conditions is equal to negative RT multiplied by the length of K, and we said that the K is an equilibrium constant, and we know how to get this one. This is the product's concentration over the reactant's concentration. Every one of them is raised to the power of its coefficients, and R is a fixed value. This is the gas constant, that's 8.31. This is in joule per mole per Kelvin, joule per mole Kelvin. The length of K, this is the equilibrium constant, and the T is the temperature, the absolute temperature, or the temperature in Kelvin. Okay, and we try to relate the reduction potentials and the electrochemical cells to the entropy, and we said we revised how we can have a reaction which is spontaneous in the electrochemical cell, and in this case it will have a positive E node net that is equal to a positive value, and this means that the entropy for it, or the delta G, will be negative value. And we said that the reverse is, this is spontaneous, or we called, by the way, we said that in the AP usually we don't say spontaneous too much in the AP. We usually say thermodynamically favored. So thermodynamically favored instead of saying spontaneous. The opposite of this reaction will have an E node net of its negative value, which means that it's not possible. And the delta G for that one will be positive. So it is non-spontaneous or non-thermodynamically favored. Or we can say it is unfavorable thermodynamically or non-spontaneous. This is mainly related to the AP chemistry exams. They will usually say this word thermodynamically favored or unfavorable. Okay, so we saw how the reaction is positive or negative and how this can be linked to the entropy. And we'll just try to remember how we used to find out the E node net of the cell. We said that the E node net of the cell is usually reduced by the two reactions which are happening in the cell. And the electrochemical cell contains two different electrodes. One of them should go through the oxidation process, and we usually call this one the anode, and this is usually the negative electrode. The other one will go through the reduction. This is the one that will gain the electrons, and it is called the cathode, and it has a positive charge. And usually the electrons will move from this one because this one is producing electrons by the loss. So it moves from here to here. This is how the electrons move. While the current is the opposite of this one. It goes from the positive to the negative. So the current moves like that, while the electrons moves like that. This is in the wire, of course. And if he asked me about the current in the cell, in the salt bridge, I will tell him it is the opposite of this. So it is from the negative to the positive, same like the electrons. So again, the electrons goes from the negative electrode to the positive electrode, while the current moves in the wire. The current in the wire moves from the positive to the negative, and the current in the salt bridge is the same like electrons. So it is again from the negative to the positive value. And if we need to calculate this one by ourselves, we'll go back to our table, which they will give us in the exam, and it's called again the reduction potentials. We said that the reduction potentials contain all the reduction values for any substance used as electrode. Either it is a metal or it is a aqueous salt or aqueous salt. And in this case, he will give me all the reduction potentials. So they will all be gaining electrons. They will all be gaining electrons, plus 1 electron, plus 2 electrons. Like that, they are all containing electrons, and they have different values placed inside the table. And in order to make this as a full reaction, we have to make one of them oxidation, and one of them as reduction. So we'll pick one of the two electrodes to go through oxidation and one to go through the reduction, which means that I will reverse the values of the reduction potentials that he has given to me inside this table. which one we will reverse? We'll reverse one which has usually a smaller value in the reduction potential table, or which is more negative, while the one which is more positive or the bigger value will be kept as it is to be reduction. And in order to change it from reduction to oxidation, number one, to change it from reduction to oxidation, you have to reverse the equation. So reverse equation number one, which undergoes the oxidation, and then I will add them all together. Add the E node of the oxidation plus the E node of the reduction. If the value is positive, so this means that it is possible and there will be current, and this is spontaneous or thermodynamically favored. But if I added them and they are getting me a negative value in volts, so this will be not possible. So there is no current and it is thermodynamically unfavorable. And I have to watch out because sometimes in the exams, he tries to trick me and try to put me another table. He will not give me a table, but he will give me values of the oxidation potentials. So he'll give me a group of oxidation potentials instead of reduction potentials. The same thing he will do. He will give me some values and they will all be oxidation. So he'll give me two reactions. Both of them are oxidation potentials. Like this one loses electrons, X loses electrons, and Y loses electrons also. Again, I'll have to do the reverse now. I have to reverse one of them to change it from oxidation into reduction. The same way we told the one that goes oxidation is the smaller value. Okay, we'll have to reverse here. So I will have to look for the bigger value. So I have to go look for the bigger value. Instead for looking for the smaller value or the more negative, I will look for the bigger value because this bigger value is the one that will be reversed. That's the one will be reversed. So I will just change one of them into oxidation and keep the other one as is. And then I have also to add them together. If it is positive, then it's spontaneous. If it's negative, it is non-spontaneous. We'll go through some examples, like the example of the half reaction between the zinc and silver. Sorry. So zinc and silver, this is zinc, change it into zinc ions, means the zinc has been oxidized. And then I go from silver into silver metal, which means that the silver has gained ions and it is reduced. I have two values. One of them here is kept as oxidation, that zinc has been oxidized to lost electrons and the value is plus 0.76. And the reduction is that one is gained electrons and it's plus 0.80. So I have just to add them together because they already one oxidation and one reduction. I will find the value is 1.56 volt positive. This means that it is a spontaneous reaction. If I reversed the reaction, and I made that the zinc ions are the ones that change it into zinc solid, and the silver solid is the one that's reversed and change it into the silver ions, this means that I have made the opposite of this reaction. Then I will know for sure that in this case, this will be a non-spontaneous reaction. It will be a non-spontaneous reaction. Of course, I have to keep track of the balance and the number of electrons. So this one, for example, will have lost 2 electrons, and this one will have gained 1 electrons. But since this is a redox reaction, whenever you are balancing it, you have to make sure that the number of electrons gained and lost are the same. So if you are trying to balance it, these 2 electrons here has to be matched with these 2 electrons. So you have to multiply this equation by 2. So the whole thing will be multiplied by 2. This means this will be 2 and this is 2. Don't forget in the redox reactions, always to balance the number of electrons lost. So 2 electrons lost, it will be 2 electrons gained. Okay, again, one more drawing for that reaction in the form of galvanic cell. So we have the cathode, we have the anode, everything we explained here in the drawing, how the electrons move, how the salt bridge. The salt bridge, just for knowledge, because some questions come about it, it just contains a salt. This salt does not interact with anything that's happening here. The salt is only to balance the charges. So to balance the charges. Why this is happening? Because we know that this zinc has changed into zinc ions. So zinc has changed it into zinc ions. If this zinc ions keeps accumulating like that, this will make this one more positive. So it will make it more positive, and then it starts to become more positive and positive and positive. So this causes that 1 to become positive instead of negative, to reverse the current. Instead of it is being a negative, it will be reversed and become positive. So this means that it will not work. So I have to get something that neutralizes this positive. This will come through the negative ions. So the negative ions, which is the anions in the salt bridge, will go and neutralize this zinc ions, so it doesn't become excessively plus. And also here I have too much minus. Why this one? Because of a lot of electrons came here. So I will try to neutralize this by the Na plus. The salt bridge does not interact with the charge or the electrode potential that's coming here. It only neutralizes the excessive charges to prevent the electrochemical cell from stopping. This is the benefit of the salt bridge. Okay, one more thing we took before is the non-standard conditions. All the equations that we have explained until now was talking about the E node net. E node net all happens at standard conditions. The standard conditions means that the temperature of this reaction will be at 25 degrees centigrade, and that it will be 1 atmospheric pressure, and that they will be all in a solution which is 1 molar. Like this one copper is in a solution zinc sulfate, for example, or zinc nitrate. And this one concentration should be 1 molar. So everything should be in 1 molar concentration. This is what we know as the standard conditions. But what if we are not using the standard conditions? Then we have to find the value of the E cell by the Nernst equation. So I will use the Nernst equation. This is a special equation which helps me find out what will be the E net of the cell in case of the conditions are not standard. It tells me that these conditions at non-standard conditions, which is called just E cell, is equal to the E cell, but at the standard conditions, minus R multiplied by T over N multiplied by F, and then multiplied by the ln Q. So I knew everything now. The T is the temperature in Kelvin, the Q is the equilibrium, and NF is the Faraday constant. This is the value that will be given to me, otherwise it's equal to 96550. And the number of electrons, of moles of electrons. So the number of moles of electrons. The number of moles of electrons, as we explained before, has to be adjusted so that it can contain the number of electrons lost and number of electrons gained. And we said that it has to be balanced. So if you have 1 and 1, use 1. If you have 2 and 2, use 2. But if electrons lost are 3 electrons and electrons gained are 2 electrons, then you have to match them up by multiplying this one by 2 and multiplying this one by 3. In this case, you have made them both equal. So this will be 6 electrons lost and 6 electrons gained. And the value that you will put here will be 6 electrons. So the value of the N will be 6 electrons gained and lost. The other cell that we have to revise is the electrolytic cell. We also revised the electrolytic cell before, so we said that this is a cell used to break down the ionic compounds into 2 ions, and these ions will be discharged from the container and changed into atoms by losing their charge. This ionic compound is what's known as the electrolyte, and it should be available either in the form of a molten form that's changed from solid into liquid by high temperature, and it can be also available in the form of aqueous form. And this is when you dissolve this electrolyte in water, but molten has no water. The same thing happens in both of them. The compound is broken down into the ions. So NaCl is broken into Cl minus and Na plus. And this one is made from 2 electrodes joined by the battery plus and minus. And then in this container, there is the electrolyte that's broken down. The positive ions will start to move and go to the negative electrode, and the negative ions will start to move and go to the positive electrode. According to if it's molten or aqueous, I will decide what are the atoms produced. The metals usually will change into a solid metal. This is in the case of aqueous solutions, but if it is not aqueous solution, it will be molten, so it's at high temperature. So this is solid. And if it's molten, it will be a liquid. So Na changes into a liquid because at the high temperature, it's not solid, it's just liquid. While the other ions like H plus changes into H2, this is at room temperature is gas, so it will be gas anyway. the O2 will change, the O2 minus, the oxide ions change and become O2, and the Cl minus changes into Cl2, Br minus changes into Br2, and I minus changes into I2. So everyone will change into the atomic form, and if it is a diatomic molecule, then it has to be in the diatomic form. According to what we can decide which one will be charged in the anions. In the anions, there is a high priority for Cl, Br, and I to be discharged over the OH minus. If this is available and this is available, so the priority is for this to be discharged. Discharged in the anions means to lose the electrons and gets oxidized. So the one that's here will be oxidized. If you don't have these ones and you have just OH minus and any other ions, negatives, so the priority is for these ones over these ones. This is the least one that has priority to be oxidized. And this one will be changed into O2 gas through the equation. OH minus changes into O2 gas. You have to balance this one by putting H2O. So here I have 4OH. I'm sorry. This is H2O. So I have here 4 oxygens. So I have here 4OH and 2 O2. So here I have 4 oxygens and I'm sorry, I have 4 oxygens and 4 hydrogens. Now it's balanced. I have changed the aqueous OH minus ions into oxygen gas and liquid wood. In the case of cations, I have always metals, and with the metals I have the hydrogen ions. If the metal I have is less reactive than hydrogen, then it will be displaced, like copper ions. I'm sorry, like copper ions, like silver ions, like gold ions, like platinum ions. They will all be discharged and changed into the solid. So copper solid, silver solid, gold, and platinum. If there is any other metal, then it will be more reactive than hydrogen. And in this case, hydrogen is the one that will be released. Released in case of cations means at the anode, they go to the anode and they gain electrons, so they will be reduced. So they will be reduced. So H plus gains 2 electrons, to form the hydrogen gas will be released. As we explained before, that the electrolysis is the same thing. The electrolysis is the same thing as the electroplating, is the same thing like copper refining. All of them are based on the same electrolysis process, because in all of them they have a battery. In all of them they have plus and minus. The plus in all of them is called the anode, and the minus in all of them is called the cathode. And this one in the electrolysis is connected to 2 electrodes. The electrodes are usually made from copper, carbon, or platinum, because this metal, carbon, platinum, or the non-metal carbon, they are non-reactive, means they are inert, but they can conduct electricity. I don't want them to interact, they will just conduct electricity. And here is the electrolyte. In the electroplating, I have the metal that I will use, metal used for electroplating on the plus, and the substance that will be electrolyzed to be electroplated, so to be electroplated on the right side. Like if I have a watch or anything I want to electroplate, it will be on the right side. And then I have a container. This one is the salt of the metal used. So if I'm coating with gold, then it has to be a gold nitrate salt or any soluble salt. Still, this is plus and minus. And then the copper refining, I have here the impure copper, and here I have the pure copper. And here I have a solution of copper sulfate or whatever aqueous solution of copper. In all of them, the oxidation will happen here. So as we explained here on the cation side, which goes to the anode, in all of them, here it goes the reduction. So this one is the reduction. So and this one is at the cathode, which is the positive. So all the negative ones, this is plus, and it goes to the, did I just reverse it? This is the cations, and they went to the anode, to the cathode. I just reversed this part. The cations, which are the positive ones, The cations, which are the positive ones, went to the negative electrode, which is the cathode. Yes. And this one went to the negative electrode. This is the anion. This is went to the positive electrode, which is the anode. So this means that the oxidation has happened here. The same thing will happen here. This will be oxidation, and this will be oxidation, and will be oxidation. Here there is a reduction. Here there is a reduction. So examples for the oxidation electrolysis, I have aluminum and have oxide. So this breaks into aluminum 2 plus and aluminum 3 plus and O2 minus. So the aluminum goes to the negative electrode. Aluminum ions will gain 3 electrons and form aluminum. And this is, of course, if it is molten, so liquid aluminum. This means that it has gained electrons, so it is reduced here. So it is a reduction here. And on the other side, oxidation happens on the other side. So H plus O2 minus loses electrons here at the anode and changes into O2. So this lost 4 electrons because 2 ions and form O2 plus 4 electrons. This is a gas. So oxidation here and reduction here. Example for the electroplating, if you are putting gold on the watch, then this one is the gold. The gold will be losing electrons. It is oxidation again and 1 electrons. Then it goes into the solution, and then some gold from the solution gains electrons and get reduced and be deposited on the surface of the watch. Here the copper, which is in the impurity with the impurities, the solid, falls down into the solution, so it is oxidized here, forming copper ions, and then the copper ions gets new electrons and then be changed into a solid which forms on the pure copper electrode. So this is still oxidation, this reduction. So I just need to summarize that these all are the same idea, same basic idea, where there is oxidation at the anode and the reduction at the cathode. Okay, we don't want to forget the equation that we use if you want to calculate the current. The current is equal to the charge divided by the time. And we need also to know what is the equation that we can use if we want to calculate the volume or the mass of the acid, or the volume of the liquid, the volume of the gas produced in electrolysis, or the mass of the solid which is produced as electrolysis. We'll come back to this in a few minutes. And then I have the equation of delta G is equal to minus NFE. This is the equation which is used too much in the questions from the electrolysis. The delta G, which is the free energy, the change in the free energy, is equal to minus N. This is the number of electrons exchanged, either the lost or gained, and we agreed it should be the same time. The Faraday constant is a fixed value, and E node is the value for the E node net, or the total electrode potential, or the standard electrode potential in the standard conditions. Let's have some fast examples. By this, it should be all the ideas which come, but we'll have some questions so that we can try to see. So follow this information to answer questions 1 to 5. Let's just see some multiple choice questions. So I have a reaction here, N2H4 plus H2 gives me NH3. What is the enthalpy change for the reaction number 1? This is reaction number 1. I have Na2H4 liquid plus H2 gas has formed the ammonia gas, and he is trying to find the delta HE, and he has given me three other equations. That N2H4 gives me CH4O, so this one changes into C plus CH4O reacts to form CH2O, and he has given me one more equation, the N2 plus H2 forms NH3. So how can we find the enthalpy change for this reaction? Basically, depending on his cycle. So N2H4, Mr. This is the reaction that I need to find, and I have other 3 reactions. I can say N2H4 plus CHO, so this one, if reacted, with CH4O, it's gonna form for you CH2O plus N2 plus H2. So this is the first equation. I have this value. What is this value? Minus 37 kilojoule per mole. And I have another equation, which is N2 plus H2 give me NH3. So this N2 and H2, if they react together, they will form NH3, which is minus 46 kilojoule per mole. The direction is from here to here because this is H2 is NH3 is formed by these two. Is formed by these two. So that's why we put the direction like that. But here this reacted to form N2 and H2 and CH2O. The last one is CH4O. The CH4O is formed from CH2O plus H2. So if I reacted these two, I can find out the reaction. So let me see what are the reactions that I need to keep as is and what are the reactions that we need to flip, as all the questions we have answered in the cycle, in the Hess cycle in the same way. So ask ourselves, what do I need to do with every reaction? Do I need to flip it or keep it as it is? And what do I need to do to the number of moles? Is it the same or I need to multiply it by anything? So let me see the first equation. First equation is N2H4 plus CH4O. If I looked at this equation and I look at the equations that I have, I will see that the first equation, so I can put into this H2 and, oh, this is the equation, N2 and H2. So this is N2 and H2 forms NH3. This equation, it's clear that this is the same direction that I have. I don't have to do anything with this one because this one is already the same direction. So I have NH3, NH3, number 2 moles and 2 moles. So just take this number as it is. Take this equation, so reaction 3 as it is. Why, Mr.? Because number of moles of ammonia is the same, and because the direction of ammonia is the same in the products in both of them. Okay, what about equation 2? If I looked at equation 2, I will find that there is N2H4 here and N2H4 here, the same number of moles. So again, I have just to add this one, reaction 2 as it is, and don't do anything else with it. So it is the same, reaction 2 as it is without doing anything. What about reaction 4? If I look at reaction 4, I will find that there is hydrogen here on the left and there is hydrogen here on the right. So this is left and this is right. So I will just flip this reaction and make it reverse because H2 is on the right and here on the left. So reaction 4, I will just flip it. So I will say minus reaction 4. So if I minus reaction 4, it means that instead of minus 65, it will be plus 65. And reaction 3, I will take it as it is, which is negative 46. And then also as it is, so negative 37. So add this one plus this one plus this one. The addition of all these values should give me the reaction, which is number 1. So it's equal to negative 18 kilojoule per mole. Let's see what happened when we added the reactions to prove that. This is reaction number 4. So you said you have flipped it. So it becomes H2 plus CH2O. And it formed here CH4O. And reaction 3, we did it as it is. What was reaction 3? N2 plus 3H2 forms 2NH3. And the reaction 2, we kept it as it is. So N2H4 plus CH4O has given me N2 and H2. So I clearly have this one repeated with this one, and N2 and H2 are repeated, but only N2 is 1 mole. So this is cancelled with 1 mole. And this is 3 moles. So here I have H2 here is 1 mole and H2 here is 3 moles. So I will cancel to make 2 moles of H2 and 1 mole. And right, and then H2O and H2. So H2, so this is, I have 3 moles. Yeah, now I have 3 moles of H2O, of H2. Okay, so that what's remaining is this one added to this one, 2 moles and 1 mole is 3H2. And I have here, again, did I miss anything? Again. So this is the black equation, N2H4, N, this one is reversed, so H2 and CH2O and CH4O. So this is done, the black one. And the blue one, N2 and H2, the same. N2 and 3H2 give me 2NH3, and equation number 2, N2H4 and CH4O, and N2 again, and H2. So CH4, CH2O. Yeah, there is CH2O. We forget to add CH2O here in reaction 2. N2 and H2. Let me just do it because I think I missed some of them. We'll do it again fast. We missed some of them. So again, this is minus reaction number 4. So CH2O plus H2 give us CH4O. The second one, CH4O and CH2 and CH2 and H2. This is H2, not H2O. H2, CH4O. The second one is number 2, which is N2H4 plus CH4O, and here NCH2O plus N2 plus 3H2, and the last one here is N2 plus 3H2, and here 2NH3. So let's cancel out. This is CH2O, CH2 cancelled out. CH4O, CH4O cancelled out. This is 4 hydrogens and this is 3 hydrogens, so only 1 hydrogen remains. Nitrogen cancelled with the nitrogen, and that's it. So the remaining is H2 and N2H4 from here, and N2NH3 from here, which is the same as our equation. It took a long time to prove this one. After addition of all the numbers, they will get negative 18 kilojoules. We haven't answered the question about His law from long time. That's why I'm struggling. If reaction 2 is repeated at a higher temperature, how would the reaction value for delta G gets affected? So if you made the same reaction, but you repeated the reaction number 2, and you tried to make the reaction at a higher temperature, what will this do for delta G? Now, mister, in order to know what happens in delta G, you have to see what is delta H, and we have to know also what is delta S. So, mister, you know that in order to calculate delta G, is this a positive entropy? What is delta S and what's delta H? Mister, he gave me the value of delta H. Is it negative or positive? It's negative for action 2, so negative 37. And what about delta S? Mister, you are changing liquid and liquid into gas and gas and gas. So what happens in the entropy? The entropy will increase. So we have a positive entropy and a negative delta H. What happens when you have a positive entropy and negative delta H?
It's spontaneous.
So is it always spontaneous?
No, it's spontaneous at low temperatures.
So at low temperature or at high temperature?
But at high temperature.
At high temperature. So when delta S is positive, let's review the table. When delta S is positive, when the delta S is positive value and delta H is negative value, it will be always favored. So it will be always favored. Delta S is positive and delta H is negative. This is our case, right? Delta H is negative and delta S is positive. Yeah, so it will be always favored. This means that it is favored all the time. So it will be always negative value. Okay, so I can choose the answer if it would become more negative because entropy is a driving force behind this reaction. It will become more positive because the reactants. So what happened when you increase the temperature? Mr. Delta G is equal to delta H minus T delta S. So every time you have increased the temperature, what did you cause to do? The value becomes more negative. So the value becomes more negative. You have, this is delta H for you. You said, for example, this is delta H. So this is delta H is already negative value, right? And then you multiply this value by a positive value. So let's say that this is, for example, negative value, let's say positive value, which is 100, and you keep increasing this number. So this is positive value, you keep increasing this number. So on this 20, so it become minus 200. Let's say it's minus 37 minus 200. So you keep increasing this number, minus, 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 so you keep making it more negative. So the value will be more negative. So the value delta G will become more negative because the overall value, this overall value for this one becomes negative. Right. What if number 3 says, under what conditions would the reaction 3 be dynamically favored? This reaction number 3. When it is dynamically favored. So number 3. So in this reaction also, it is reaction number 3. So let's put number 3 here. This is negative delta H. Delta H is negative, and delta S, what is delta S here?
So can you go back up to the equation?
Yep. Sorry, I thought I copied it. Someone. You are changing from gas into gas, but what about the number of moles? 1 second, I'll try to copy it here. What about the number of moles? Because you are changing from gas to gas. So what happened to the number of moles?
They decreased.
So decrease. So instead of having 4 moles on the left side, you become having only 2 moles of gas on the right side. So this is negative 46. So it means the delta S is
Negative.
negative. So we have a negative delta S and negative delta H. What will be the conditions here?
It's favored at low temperatures.
So it's favored only at low temperatures when you have negative delta H and negative delta S. Okay, the fourth one is asking under which conditions? No, this is done. So this one is a good one. If I have, if 64 of CH4, and we'll also copy the equation better than making this a very big page. So this is reaction 4. He's saying if this 64 grams of CH4O were decomposed via reaction, approximately how much energy would be released or absorbed? For sure, is it released or absorbed for sure?
Released.
It is released because the delta H is negative. We are sure that it is released. It will never be absorbed. But how much is the value? Mr. He is telling me that delta H means per 1 mole of the substance, it's negative 65 kilojoule for 1 mole only. How many moles I have here? I have number of moles is equal to mass over molar mass. The mass is 64 grams. And what is the molar mass? That's carbon, which is 12, and hydrogen 4. So it is 4, and oxygen is 16. Is this 32? So 32, 64 over 32 is equal to 2 moles. So if I have 2 moles, what will be the amount of heat that's absorbed or released? I just have to double the number, right? So 2 multiplied 65 divided by 1 is?
Negative 130.
Negative 130. The value, the sign will be as it is, and we are sure that it is released and it will stay negative because this is an exothermic reaction. So negative 130. This is the correct option, number D. So a 2-liter flask holds 0.40 grams of helium gas. If the helium is evacuated into a larger container, while the temperature is held constant, what will be the effect on the entropy of the helium? So this is the flask. The flask contains helium, which is 0.40 grams of this helium. The helium is evacuated into a larger container. So it's removed and put in a bigger container. Instead of being here, it becomes in a bigger container. And the temperature is the same. What will be the effect on the entropy of the helium if I did like that? Is it going to be the same? I did not change the number of moles. Or is it going to decrease because the gas will be more ordered in a larger flask? Or it will decrease because molecules will collide with the sides? Or it will increase because the gas molecules will be more dispersed? I think that's easy one. The gas particles, of course, will be more dispersed. It will, instead of they being contained here. So they are still gas and it is unarranged and it has a high entropy, but here it becomes even more dispersed and less arranged. So it is gas and it's still a gas, but it becomes more disarranged or more random. You give them a chance to run everywhere and become more random. That's why they will be more dispersed and the entropy is going to increase. So the entropy will of course increase because the molecules are more dispersed. So he has given a reaction and said this is not thermodynamically favored, which means that they are not spontaneous under standard conditions, but it becomes thermodynamically favored as the temperature decreases towards the absolute zero. Which of the following is true at the standard conditions? Mr. He's saying that it's not thermodynamically favored under standard conditions. So you want to say that delta G is positive value, but it becomes thermodynamically favored as the temperature only decreases towards the absolute zero. So what do you want to say about the delta S and delta H? The same way we have just answered a similar one right now. Right, we have answered a similar one right now, which is delta H and delta S are both what? Negative, right? Yeah, and we said that when both of them are negative, it will be only at low temperature that it becomes thermodynamically favored, only at low temperatures if they are both negative. So you want to say, Mr. This will be delta G, of course. So this will be at negative only if it is at low temperatures, and it will be positive delta G if it is not favored and a high temperature. And he said that here it is not favored. So he told us that this is not thermodynamically favored. It will be only favored if what? If it is negative delta G, and this happens when they are both negative. I cannot say both positive because if it is both positive, it will be only favored at high temperatures, not low temperatures. Okay, right. So the answer, of course, is A. So which of the following statements accurately describes the above reaction? The entropy of the reactants exceeds that of the products. This you want to say that the entropy has decreased. So let's see, this is a gas and this is a liquid and this is a gas and this is a gas. This means that the entropy has increased, of course, and you are saying that the reactants is more. So this is wrong. It cannot be more because you are saying that it has increased while it decreased while it increased. So you are saying here that entropy decreased while we say it is increased. H2O will always be the limiting reagent. Why will be the H2O always be the limiting reagent? Is there anything that tells me like that?
No.
No, you have to tell me what are the amounts of moles that you have used so I can decide if it is limiting or no. It can be always excess or limiting. It depends on how much I have used. This reaction is never thermodynamically favored. Mr. The delta S is
Positive.
positive value, increased, and delta H is
Negative.
negative value. What happens when the delta H is negative and delta S is positive?
It's favored.
Yeah, it's favored. It's favored. Actually, it is always favored, right?
Yeah.
Delta. Okay, the temperature of the surroundings will increase as this reaction progresses.
Yeah.
Yeah, because it is a what?
Exothermic.
Exothermic mode. So it is an exothermic reaction. So for sure, once we increase the reaction or the reaction progresses, it will be releasing more heat to the surroundings. Right, which of the following is true for this process at STP? Let's make some copies. So still we have much. Which of the following is true for this process at STP? The value for delta S is positive. This one has changed from liquid into solid. So of course it is negative, not positive. So delta S is negative. The value for delta G is 0. Is the value for delta G is 0?
No.
Mm,
Isn't delta G 0 only at equilibrium?
Yes. And when does the equilibrium happen? At the phase change.
Oh, yeah.
Yeah, at the phase change, at the temperature in which the boiling happens or the melting happens, when they keep changing, not one of them is favored over the other. So not one of them is favored over the other. They are at equilibrium. So the value of delta G is 0. That's correct. The value for delta H is positive. Is this correct?
No.
Mister, you are making a solid from the liquid. So you are freezing here. And when you are freezing, you are making bonds. And when you are making bonds, you are releasing heat. So it should be negative delta H, not positive delta H. And the reaction is favored. Is this reaction favored?
No.
Why it's not favored?
Because you're going from liquid to solid.
Okay. You are, what did he say? He gave me a very small point that will help me. What did he say? He said, when this is happening, a very small note. What
at
did he?
STP?
He said at STP, and this means that we are at 25 degrees, or which degrees?
22.4.
No, 22.4 is the molar volume. But what is our temperature?
$25 or 27?
Our temperature is 0 degrees. Huh? Isn't this the temperature that the freezing happens?
Yeah.
But I still cannot say it's favored. Why? Because I just said that this is a what? A phase change where delta G is 0. So nothing is favored. You cannot say anything is favored. If you are at 0 degrees, you cannot decide you are melting or you are freezing. You cannot decide. You are at 0. Only if you become at a temperature which is higher than 0, then you can tell me that I am melting. And if you come at a temperature which is like anything 1 degree centigrade, I am melting. What about -1? I am freezing. I am freezing. But if you are at 0, you cannot tell me that I'm freezing and or melting. The same like we are doing before in the cooling curve and the heating curve, right? So I am here at the 0 degree centigrade. This is the point that I'm talking at. This is the line, right? I'm here. Are you melting or freezing? I will never know. It depends. Are you heating or are you cooling? If you raise the temperature above 0, I am melting. If you decrease the temperature less than 0, I'm freezing. You are at 0, nothing is favored. I am what? Equilibrium. Delta G is equal to 0. Okay? Right. This concept is very important to understand because it solves a lot of questions. I have to put it in my mind very well. The equilibrium idea. In which of the following reactions is entropy increasing? Okay, I think we can just pass this question. It is a very basic idea. The reaction
D.
is yeah, it's D. Very good. So this one gases has changed it into. Since we answered it, gas has changed it into gas and gas. The rest here is 2 moles, 3 moles. Here 2 moles into 2 moles. No change. I cannot decide here, by the way. So I cannot decide unless he give me numbers. Okay. I cannot decide unless he give me numbers. CO and H2, 2 and 2, and here 3 and here 3 and 2. So this one is decreasing. So this is the only option in which it is increasing. Okay, this is a good one also. Ideas that will come. In which of the following circumstances is the value for K equilibrium always greater than 1? Which is the value that it is always greater than 1?
So, Mr. Here, it's favoring the products. Right?
Okay. Okay.
So delta H is negative
Okay.
and delta S is positive.
Delta H is negative and delta S is positive. Very good. Again, why?
Because you are favoring the right side, the products are increasing. And temperature increases because it's exo.
Okay.
And delta S is positive.
Excellent, Montez. Okay, I have one more idea, which is which expression will calculate the mass of copper that can be placed out. Yeah, this is very good electrode. This one. I have copper electroplated out of 1 molar copper nitrate using a current of 0.75. Which expression can be used to calculate the mass of the copper? I need to know how much copper is deposited while I'm electroplating. Which equation should I use? The time in what? In seconds, and here I have the time in minutes, so multiplied by 60 multiplied by what? The current, which is 0.75 multiplied by
I forgot the equation.
the molar mass divided by the F and
Number of electrons.
Number of electrons. So divided by, multiplied by the molar mass of what? The molar mass of what?
CuNO3.
Cu only, the metal only, which is depositing. Only Cu, 63.555. The molar mass of the metal being deposited only, divided by F, and F is 96500, and multiplied by the number of electrons of what? Both of them, or only the substance which is depositing? Only the substance which is depositing. So copper 2 plus gains 2 electrons and give me copper. So here is how many electrons? 2. I don't care what's happening on the other side. So I don't care if there is copper, which is gaining 2 electrons, and I have with it aluminum, which is losing 3 electrons. I don't care about this one. I care only about my metal. So my metal in the atomic mass and my metal in the electrons. This is different from what I'm doing here when I'm doing when I'm calculating NFE in the nearest equation, and here I'm using what? The number of electrons in both reactions. Number of electrons in both reactions. So moles of electrons gained or lost, it has to be in both of them. So if one is lost 3 and one is gained is 2, I have to make them the same thing. Okay. And so it's A, of course, the answer, if I didn't mention. If I didn't mention, the answer is A. Okay. طيب. What is the general relationship between temperature and temperature and entropy for diatomic gases? Does the temperature affect the entropy for atomic gases? They are completely independent of each other. Temperature has no effect. There is direct relationship because at higher temperature, there is increase in the energy dispersal. There is inverse relationship at higher temperature, more likely to be a gaseous state. It depends on specific gas and strength of the intermolecular forces between individual molecules. He is talking about diatomic gases specifically. So he's talking about that one specifically. So I will say, of course, at higher temperature, the gas becomes more dispersed. The gas becomes more dispersed. Okay, I think we have a couple of more questions and some free response questions. That's too much to finish today. So I think we will just finish the next time so that we will be having three times for these chapters, and it deserves chapter 18 and 19, 17 and 18. So hopefully we'll finish them next time. Okay, I'll just stop the recording. 1 second.